Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. In this video, we will continue our exploration or our review of exponential and logarithmic functions by dipping our toes into logarithmic functions. We've already gone through a review of exponential functions, their graphs, their equations, kind of the forms of them, that type of thing. Now we are moving into the second half of that, and likely the most important of the two, which is logarithmic functions. Again, it is assumed that you've seen all this stuff before, so I'm just going to do a quick review of what you've seen in the past. So starting with the definition of a logarithmic function, base b. The logarithmic function with base b is defined by the following bijection. This is known as a bijection when you see this symbol right here. We also call that an if and only if, and we use this kind of shorthand for it, if and only if, which basically says this notation, log base b of x equaling y, is true if and only if b to the y is x. Another way to say that is, if log base b of x is equal to y, then we could rewrite that as b to the y is equal to x. And if b to the y is equal to x, we could rewrite that as log base b of x is equal to y. The way I always learned this when I was a student, or the way I remembered it, was via something called the circular argument. B raised to that y should equal the argument inside. B to the y, which let me highlight that, should equal the argument x. So it does make sense to write it that way and call it the circular argument. A few notes about the logarithm base b. The base itself must be positive. Now let's focus in on that right now and talk about why that base must be positive. It's from the natural definition of the exponential function. The base for this exponential function that you see right here is the exact same base as we have for the logarithm. And by definition for an exponential function, the base must be positive for an exponential function. That is why the base must be positive for the logarithm as well, because it's the same base. Likewise, the base cannot be 1, again, because the exponential function, b to the y is equal to x, or exponential equation, I suppose. But anyway, the base for that exponential being b cannot be 1 by definition. It would not be exponential. If it were 1, then it would just be a constant. 1 to the y is always just 1. And so it would not be an exponential function. It would be a constant function. So those are the conditions on b. It cannot be, it must be positive, and it cannot equal 1. Since x is the output of an exponential function, let me highlight that right there, that x cannot be negative, nor can it be 0, because exponential functions are never negative and they never return 0. And I should say, never is a really dangerous word, but base exponentials, b raised to a power, that is always going to return a positive number. Therefore, x will always be positive. And that x is the same x that is playing the role of the argument for the logarithm. So the argument for a logarithm must always be positive. That's so important that I would like to actually write that down below, even though it's already written there. The domain of y equals log base b of x is 0 to infinity, not including 0. So basically all positive real numbers. It's critical that you understand that, mainly because that's going to be the end all be all for all your work with logarithms in the long run. You need to remember, logarithms, their arguments must be positive. And I said all that, and then I switched to the next page here and realized, I say it again in this next page. That's how important it is. The domain of the logarithmic function f of x equals log base b of x is positive, all positive numbers. So all x greater than 0. The range, on the other hand, is negative infinity to positive infinity. And if you don't recall, perhaps I should just go ahead and jot down a graph, even though this is technically not where you would learn the logarithmic graph. The fact is, you guys have already seen the logarithms and their graphs, so I can go ahead and just jot down the logarithmic graph right there. Notice that there is a vertical asymptote at x equals 0 here on the vertical axis, and that our function will never touch that vertical asymptote. Again, because functions don't touch their vertical asymptotes. So if that was the y-axis, you could see that the domain, the set of x values that we can plug in, could be any x value here, all the way up to and including, or down to and including, all the way down to but not including 0. Because again, x equals 0 is on the vertical asymptote, so you can't plug that in. As far as y values go, the range, notice that, and I'm going to go ahead and highlight this, and maybe in this color right here. Notice the y values will dip as low as you want them to, and they'll climb actually as high as you want them to. So the y value is represented by this blue curve. It'll keep climbing forever. It's a very slow growing function. Logarithms are, they're incredibly slow growing, but they fall very quickly as you move to the left. So the range of the logarithmic function is all real numbers. The domain is just all positive real numbers. A couple other things to note before we get into some examples. You should recall that there is a very special base for a logarithm called, which is base 10, and we call that the common logarithm. So the logarithmic function base 10 is defined to be the common logarithm. It's denoted log of x rather than log base 10 of x. And that is just because, well, it's a very commonly used logarithm, but not in the sciences. It is commonly used in engineering, log base 10 is, and also, I guess, in sensory problems like decibel problems and Richter problems and stuff like that. But generally in the sciences, so if you're going to science, you'll be using the natural logarithm, and that is actually the next page over. Now, if you feel as though I'm going quickly through this, well, it's probably because of two things. One, I know I speak very quickly. That's just my problem. You can always use YouTube to slow me down, okay? The other thing, reason why I'm going very quickly is because, well, this should be a review. If you need a deeper review of this content, you should watch my videos on Algebra 2. I have a full derivation of all of this stuff in my algebra videos, which are they're basically high school level algebra classes, not transfer level. So you're in transfer level, you should already know this is the mindset. Now, as I said, this next page is a natural logarithm. Again, you've seen this before, but probably not have played with this very much. The logarithmic function with the very special base e, which we talked about in a previous lecture, is defined to be the natural logarithm. It's denoted with ln of x rather than log base e of x. And if you're wondering why it's ln, a lot of people think, actually, I don't know what a lot of people think, but it's French, logarithm naturel. So that's why we use ln. Even though it looks like a 1n, it's an ln. All right, all of that precursor material done. Let's go diving into some examples here, just to remind ourselves how logarithms work. The very first set of examples. Write each of the following logarithmic equations in exponential form. Basically, what I'm asking you to do here is take a log base b of x is equal to y and use the definition of the logarithm, the circular argument, b raised to the y is equal to the interior. So you would rewrite that as b to the y is equal to x. So each of these we'll do that with. For example, log of, what is that, million, billion, 10 billion. Log of 10 billion. Well, the hidden base here, because I didn't explicitly state it, is 10. Whenever you do not have a base stated, it is always assumed to be 10, unless it's the natural log. And the circular argument tells us 10 raised to that 10th power should equal the interior. So we're going to trade out this logarithmic equation for its like kind exponential equation. And this would imply that, again, by the circular argument, 10 raised to the 10th is the same thing as the argument, which is 10 billion. Those two statements, the blue and the typeset statements, are identical statements. They mean the same thing. Moving forward, log base 5 of 625 is equal to 4. Again, all you're using is that circular argument. 5 raised to the 4th should equal the argument inside. So this will imply, when you write this as an exponential equation, 5 raised to the 4th should equal the interior. You're not really solving anything, you're just rewriting these. You have to really get used to rewriting logarithms in exponential form and vice versa. The reason why is because you'll need to transform between them very quickly within problems. And so you just need to know how to do that. The very last one here, the natural log of e to the 5th is equal to 5. Remember, there is a hidden base, it's base e. So by the circular argument, e to the 5th should equal the interior. Now notice, this is going to seem like a silly statement, but this is the same thing as saying, again, e to the 5th is equal to the argument, which is, by the way, e to the 5th. It's a silly statement, I totally get that, but there you have it. Now let's go in the other direction. Let's say we started with exponential functions and exponential equations, and we needed to rewrite them in logarithmic form for one reason or another. Who knows? Just remember, I think it's much easier to go from logarithmic form to exponential form than it is to go from exponential to logarithmic, and I often forget, honestly, how it's done. But one thing that I can state here is the base of the exponential is the same as the base of the logarithm. So I'm going to go ahead and write that. I know I have a log base 2 in this example, and I have a log base 10 in the other example. We don't actually have to write that base 10, but I'm going to. And then I'll put some parentheses and an equal, parentheses and an equals. And remember what the circular argument would tell us. 2 raised to that power should equal the inside. Ah, that tells me exactly what I'm doing. 2 raised to the 10th. Ah, okay, so this here will be a 10, should equal the inside. Okay, so should equal 1024. I specifically, by the way, chose this exponential equation because 2 to the 10th is incredibly important to know. It's not that you have to memorize all powers of 2. You certainly cannot do that. However, 2 squared, 2 cubed, to the 4th, to the 5th, those are important. 2 to the 10th is really important. If you think about, let's say that you're a computer science major. 1024 should be a very special number to you. How many bytes are in a kilobyte? How many megs are in a megabyte? Right? How many gigs are in a gigabyte? Actually, I should say that the other way. How many kilobytes are in a megabyte, and how many megabytes are in a gigabyte? and how many gigabytes are in a terabyte. That's what I was looking for. They're all the answers are the same, 1024. It's because computers work on gates. Gates are either open or close, so there are only two options, and they work in powers. So they work in powers of 2, and generally, when you're dealing with words like kila and mega and giga and tera, they're powers of 10 away from each other. So it's 2 to the 10th, which would be 1024. So anyway, that's a very special number in computer science. That's why I like to pick on that. Anyway, back to what I was doing. Sorry for the diatribe there. The other one down here, remember, 10 to a power should equal the inside. Well, what's the power on 10? It's 5. In the interior, it's 100,000. Well, you can double check your work. 10 to the 5th, 100,000. That's what they told us. Okay, I'm fine. And that's all you need to do to transform from an exponential equation to a logarithmic equation. It's not too terrible. And finally, in this video, we're not going to do a ton of properties of logarithms. That will happen in the next video. In this video, it's just the basic ideas of what a logarithm is. So if I asked, what's log base 121 of 11? It's easier, honestly, to say, that's some value I just don't know. Because then you can rewrite it in exponential form by saying 121 to that power x should equal the argument. Let me write that down. 121 to that power of x should equal the argument. Well, notice 11 and 121 actually have something very much in common. 121 is the same thing as 11 squared. So this implies we have 11 squared to the x is equal to 11. Well, that means, using laws of exponents, that 11 raised to the 2x must equal 11 raised to the first. And that means that 2x must equal 1. If the bases are the same, then their exponents must be equivalent. And that tells me that x must equal a half. Now, you might have gotten to that answer or arrived at that answer without going through all that rigmarole. Because you might be able to see that, hey, listen, 121 to the 1/2 power, yeah, that's 11. And so then you really can, if you start thinking of it that way, it happens much faster. So 2 raised to what power is going to be 1024? Well, this is the one I was picking on earlier. It's 2 to the 10th power is 1024. And e raised to what power is the square root of e? Well, e to the 1/2 power is the square root of e. So these are kind of the fast ways to do it. So you're looking, if somebody just hands you a logarithmic expression like this that involves constants, you're really looking for what's the power on 121 so that it becomes 11. Well, obviously it's not going to be a power 1 or greater because that would just make 121 larger. So it has to be a fractional power less than 1. That's how you do these problems. They're all not too terrible. And it is a massive review. So I'm just quickly kind of restating stuff and trying to jog your memory before you head into the deeper depths of logarithms.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.